Is my screen visible? Is it visible?
Yes, sir.
Yeah, okay, right. So welcome back to the class on advanced design of steel structures. So in the previous class, we done with one numerical example where the design of a beam column was involved. But that problem was like the column was subjected to only uniaxial compression and it was subjected to only axial compression and uniaxial bending moment. Now we shall see a numerical example where the column is subjected to the compression, and along with that it is also subjected to biaxial bending moment. So let us proceed. So now a non-swift intermediate column in a building frame with a flexible joints is 4 meter high. The column height is 4 meter. And the section of the column is ISHB 300 at the rate 588 Newton per meter. Check the adequacy of the section when the column is subjected to following load. So it is subjected to a factored axial load of 500 kilonewton. That is the compressive load which is passing through the center. It is subjected to a load of 500 kilonewtons. Okay, then it is subjected to the bending moments. Now how are those bending moments is just wait for a minute, hang on. Okay, right. So it is subjected to biaxial bending moment along the major axis, that is mz. The bending moments are at the bottom it is 7 kilonewton meter and at the top it is 15 kilonewton meter along major axis. Now along minor axis, at the bottom the bending moment is 1 kilonewton meter and at the top the bending moment is 0.75 kilonewton meter. Now you have to take the yield strength of steel as 250 Newton per mm square and the Young's modulus as like that. Now you have to assume an effective length of the column as 3.4 meter. Okay, actual length of the column is 4 meters, but you have been asked to consider effective length of the column as 3.4 meter along both the axes. Okay, so this is the problem statement and you have to check whether the section ISHB 300 is capable of taking all these type of loads. Okay, right. So I will try and make you understand how the loads are being applied. Okay. So what I will do, I will draw the column. I'm showing you the just the face of the column. Means this is the flange of the column, what you're seeing. Now it is being subjected to an actual compressive load of 500 kilotons. This is also 500 kilonewtons and this here is also 500 kilonewtons. I will not draw a break line. So this I will take it as the end lines itself. So now the length of the column, the effective length of the column, what you have to take is 3400 millimeters. Okay. Now what I will show is the top and bottom sides. I will draw the I section now. So assume that this is an I section. This is the at the top. Okay. Let me mark the axis here. This is the major axis, that is call it as ZZ, and this is the major axis, minor axis, call it as YY. Now along major axis, you can see at the top, along major axis at the top, that is MZ, the bending moment is 15 kilonewton meter. So the bending moment will be acting along the major axis, 15 kilonewton meter. Now along the minor axis at the top, it is 0.75 kilonewton meter. Okay. Now similarly, if I try to draw at the bottom, it is like this. This is your I section. This is the, sorry. This is the major axis, ZZ, and this is the minor axis, that is YY. Now this I'm drawing at the bottom. Okay. So at the bottom along major axis, it is 7 kilonewton meter. Now at the bottom along minor axis, it is 1 kilonewton meter. Okay, so this is how it has been subjected to different types of loads. Of course, the 500 kilonewton will be acting exactly at the center. The 500 kilonewton axial compressive load will be acting exactly at the center. So you may ask me how these type of loads could be acting on a column. Now, these type of loads could be acting on the column because of the connecting beams. Suppose say this is your column and one beam is getting connected like this, and another beam is getting connected like this, and one more beam is getting connected here at the bottom. Okay, so there could be one more beam which will be connecting here, means it will be coming out of the paper, which will be coming out of the paper. So because of these two beams, there will be a bending moment along the minor axis, and because of this beam, there will be a bending moment along the major axis. So likewise, the column could be connected from all the four corners. So because of that, it will be subjected to biaxial bending moment. Okay, are you clear, students, regarding how the loading is there? Are you clear? Is it clear?
So explain once again.
No, which part you want me to explain?
So that moments on top and bottom.
Yeah, see here. Uh, I'm showing just the cross section of the column at the top, and this is the cross section of the column at the bottom. So now I'm marking ZZ axis as the major axis and YY axis as the minor axis. So you can see here at the top along major axis, the bending moment is 15 kilonewton meter. So that's what I have written here. And at the top along minor axis, the bending moment is 0.75 kilonewton meter. So that I have marked here. Now in the bottom section, this is major and minor. So at the bottom section along major axis, the bending moment is 7 kilonewton meter. I have marked 7 kilonewton meter. And at the bottom along minor axis, the bending moment is 1 kilonewton meter, and I have marked 1 kilonewton meter. Now don't go with the sign conventions here. Means I'm telling you not to go with the direction of the movement. Just the directions of these movements are indicative purpose. They doesn't relate with the signs whatever they have given. They are just indicative. Means along which axis the bending moments are acting. I have told that. Are you clear now?
Yes, sir.
Okay, right. So now the section is already given to you, which is ISHB 300. So I have noted down the properties of ISHB 300. Some more properties will be required. So that I will tell you once I come to that point of view. So these are all the properties of ISHB 300 section. So first let us classify the section, whether it falls under plastic, compact or semi-compact. So epsilon is given as under the root 250 divided by Fy. So it is 250 by 250. It comes 1. B by TF is, that is the outstanding width of the compression flange. The width of the compression flange is actually 250. So you have to take 250 divided by 2 and divided by the thickness of flange, which is 10.6. It is getting out to be 11.8. And D by TW is actually, D is the total depth minus 2 times the thickness of flange divided by the thickness of web. It is coming out to be 36.62. And since it is less than 15.7 epsilon and this is less than 42 epsilon, you have to refer the table 2 of IS 800 2007. This we have already done in the previous example, and I can see that our section is a semi-compact section, because this will be required in our further calculations or further formula, whatever we write, that we want to know whether the section falls under plastic, compact, semi-compact sections. So now I came to know that our section falls under semi-compact sections. Okay. Now the first check what I have to do. This is the first check what I have to do. The first check is check for resistance of cross section to combined effects, which falls under class 9.3.1.3 of IS 800 2007. This I have already told you in the previous numerical example. This is the main equation what we have to use. Now since here the column is subjected to both your bending moment along both the axes, so the full formula I have to utilize. In the previous example, it was subjected to only a uniaxial bending moment, and that bending moment was acting along the major axis. So I took only these two terms in the previous example. Now in this case, it is subjected to the bending moment along minor axis also. So I have to take this term also. That's what I have written here. And N divided by ND plus My divided by MDY plus Mz divided by Mdz, and the summation of this should be less than or equal to 1. Okay, let us proceed. So the value of N is actually the force what you have already applied on that. So how much force, how much actual force you are actually applying? You are applying 500 kilonewton. So N should be 500. Okay, N should be 500. Nd is given by this equation, that is Ag into Fy divided by gamma m naught, where Ag is the gross cross sectional area, and the gross cross sectional area is actually 7485. That is a ISHB 300 cross sectional area. This multiplied by Fy is 250 divided by gamma m naught is 1.1. So this you will get it as, let me just calculate that. So 250 divided by 1.1 multiplied by 7485. So this I'm getting 1701. 1701.1 kilonewtons. Okay, so I am able to find N and Nd. Then let me find out My. My is the bending moment along minor axis, and I have to take maximum bending moment. Okay, out of bottom and top. So out of bottom and top, the maximum bending moment is 1 kilonewton meter. So that My will be 1 kilonewton meter. And Mz is the maximum bending moment along major axis at the bottom and top. So the maximum is out of 7 and 15, it is 15. So I've taken 15 kilonewton meter. Then, so these two are given. So you are able to find this My and Mz. Now I need to find Mdy and Mdz. So the Mdz is given by this formula, that is elastic section modulus along major axis multiplied by Fy divided by gamma m naught. And you know what is the elastic section modulus along major axis? It is given here, 863.3 into 10 raised to 3. So that you have to use. So let us just put that here. 863.3 into 10 raised to 3 multiplied by Fy is 250 divided by gamma m naught is 1.1. Okay, so let us calculate that. So 250 divided by 1.1 multiplied by 863.3 into 10 raised to 3. So I'm getting 196.2 kilonewton meter. Okay, similarly you have to use ZEY, that is elastic section modulus along y-axis. So this you can get it from steel table and it is 175.5 into 10 raised to 3. 175.5 into 10 raised to 3 multiplied by 250 divided by 1.1. So 250 divided by 1.1 multiplied by 175.5 into 10 raised to 3. So I'm getting 39.88 into 10 raised to 6 kilonewton meter. So let us substitute all these values here. So N is 500, ND is 1701.1, 1701.1. Then I have My is 1, MDY is 39.88, MZ is actually 15 divided by MDZ is 196.2. You can get here everywhere the denominator is more than the numerator. Of course, you should get less than 1. Let us check. So 500 divided by 1701.1 plus 1 divided by 39.88 plus 15 divided by 196.2. So I'm getting 0.395. And hence it is safe against combined effects. Are you clear, students? This check. Any doubts you have? Are you clear? Am I audible? Are you clear, students?
Sir, that my we have to take minus or plus only.
No, that you have to take plus only, because see here what has happened. This minus sign actually indicates you means in which sense the bending moment has been applied. Okay, in which
Okay.
sense, whether it has been applied in the clockwise direction or anti-clockwise direction, in that sense it tells you. Okay, that minus you should not take here.
Okay, sir.
Okay, they everywhere you have to take the absolute values only. No
Okay.
signs you have to take. Okay.
Okay, sir.
Right. Okay, so once it is done and you came to know that it is less than 1, hence the section is safe against combined effects. Means this check ISHB 300 has passed. Now let us do the second check, wherein we'll be doing check for the resistance of cross section to combined effects of buckling. Okay, let us do that. So here we have to determine the values of PDZ and PDY and check whether both the PDZ and PDY are more than the 500 kilonewton of compressive load. That we have to check. So once again, same thing what we did in the previous example. So KLZ and KLY are 3.4 meters, because in the numerical example only they have told take effective length of the column as 3.4 meter along both the axes. Along both the axes it is same. So I'm taking KLZ and KLY as 3.4. KL represents the effective length. KLZ and KLY represents the effective length of the column in both the axes. So in both the axes they have told to take 3.4 meter itself. So I'm taking 3.4 only. Okay. Next, I need to find the slenderness ratio in major and minor axes. So KLZ is 3400. Sorry. So KLZ is 3400 divided by RZ, where RZ is the radius of gyration along the major axis and it is 129.5. So 3400 divided by 129.5, I'm getting 26.25. Similarly, KLY is also 3400 divided by radius of gyration along minor axis that we have already noted down here. You can just see here. Radius of gyration along minor axis. Okay, I have noted down here, but you can get it from the steel table. So from the steel table, it is 54.1. Okay, so 3400 divided by 54.1, you're getting 62.84. Right, 62.84. Then you have to check whether the ISHB 300 along major axis and along minor axis falls under which category. For that, you have to check first the ratio h by b, where h is the total depth of the section and b is the flange width of the section. So 300 divided by 250 is 1.2, and thickness of flange is of course less than 100 millimeters. So your section will be, I will just show you that table once again. In the first numerical example, I have pasted that table. Yeah, here it is. You can see. So h by b is less than or equal to 1.2. So in our case, h by b is equal to 1.2 and thickness of flange is less than 100 mm. So along once again, same thing along major axis, you have to refer table 9b. Along minor axis, you have to refer table 9c. Same thing will come here. So that same thing I have written here also. You can see. So refer curve B for major axis and curve C for in minor axis. Means I mean to say the table 9B for major axis, 9C for minor axis. So therefore from table 9B, okay, for KLZ by RZ equal to 26.25. And Fy equal to 250 Newton per mm square. I need to find the value of FCD. So let us check. So I have to refer table 9, 11. Yeah, here it comes 9B. Yeah, 9B. So ours is a 26.25 and 250. So I will take 26.25 as 25 itself. So because I can do interpolation clearly, but or else you can take approximate also. So 20, it should fall between 20 and 30. So for Fy equal to 250, that is bin. So your FCD will be in between 225 and 216. So 225 plus 216 divided by 2 means I'm taking average value. So it comes to 20.5. Have you got this, students? How I'm referring this table? My KL by R is 26.25. I'm considering it as 25. So 25 lies between 20 and 30. And for Fy 250, so this column you have to refer. So for 20 it is 225 and for 30 it is 216. So 25 lies in between these two. I can take average of 225 and 216. It comes out to be 220.5. So let me just write down that. So PDZ is actually FCD, that is 220.5 multiplied by the cross sectional area, that is gross cross sectional area, that is 78485. So 220.5 multiplied by 7485, which comes out to be 1650.4 kilonewtons. 0.4 kilonewtons. And since this is more than 500 kilonewtons, hence it is okay. Now similarly, I will refer table 9C. So my KLY by RY will be 62.84. And for Fy equal to 250 Newton per mm square. So now let me refer table 9C. This is table 9B. I will refer table 9C. So 62.85, I will consider it as 60 itself. So for 60, it is for 250 megapascal, it is 168 Newton per mm square. So this value I have to take. So PDY is 168 multiplied by 7485. That is the cross sectional area of ISHB 300. So 168 multiplied by 7485, which comes out to be 1257. 0.4 kilonewtons. And since this is also more than 500 kilonewtons, it is okay. So hence the section is safe from combined effects of buckling. Are you clear, students?
Sir,
Yes.
so what if the check fails?
If check fails, you have to go for the revised section. You have to go for the revised section. You have to go with next higher section. But in this type of numerical example, usually the check will not fail. Why? Because I will tell you, they have told you to check whether this ISHB 300 is safe, right? So if check fails here itself, then there is no question of calculation of further. You can say the given section of ISHB 300 is not adequate to take the loads which are coming on that. So you can stop there only, right? So usually in these type of numerical examples, the check will not fail and everywhere it will pass only. But you have to prove that. But in case of design problems, what we did in the first numerical example, there are chances that your check may fail. So you may have to try next higher section and proceed further and come up with the section, adequate section, which will take all the loads. Are you clear?
Yes, sir.
Yeah. Okay. So any other doubts you have? Okay then. So let us go with the next check. That is the third check. This is the third check where we'll be checking for the member buckling resistance in bending. Okay, let us do that. So now here MdZ is given by the formula beta B ZP into FBD. And for semi-compact sections, you know, beta B is given as ZD divided by ZP. If you substitute this here, that ZP and ZP will go. So you will be left out with MdZ equal to ZE into FBD, where ZE is the elastic section modulus. Okay. And how to find FBD? FBD can be found using this. We have already done all these things. MCR equal to, see, in the first numerical example, I gave you one more way of calculating MCR. Okay, either you can adopt that or you can adopt this procedure. Okay, this procedure is same as the one where we used to do in first module, right? So I will go with this procedure, or you can refer the procedure what I have given in the first numerical example, where I used to calculate FCRB, and based on FCRB I used to calculate MCR and all. But here you can directly calculate the value of MCR. Okay, so pi square E is as it is. Iy is the moment of inertia along y-axis. HF is the height of the web. LT is the effective length. Okay, and all other things. So let us substitute each one by one. So this is pi square E. I will write as it is multiplied by Iy. Iy is actually the moment of inertia along y-axis. So which is 2193.6. Students, what I will do, we have some, we are actually in college now. So we have some work in the college now. So there is some videography going on. So what I will do, I will just stop the class here now. So I will proceed with the this numerical example in my next class. Okay.